Classical optics operates on the assumption that light travels in perfect, rigid lines. When an object blocks those lines, it creates a macroscopic shadow with a stark, clearly defined geometric boundary. Sound waves, by contrast, behave differently. If you stand in an adjacent room while music plays, the sound easily bends around the corners of the doorway and fills the space. Since light and sound are both wave phenomena, their behavior should be identical when encountering an obstacle. Yet light appears to shoot straight past the doorframe, seemingly refusing to bend. In reality, light bends around corners. We simply struggle to see it because the wavelength of visible light is roughly 1,000 times thinner than a human hair. Zooming in closely enough reveals that the perfect physical boundary is actually fractured and blurred. The straight lines of ray optics and the perfectly sharp shadows of our daily lives are an optical illusion created by our macroscopic scale. When light hits an opening or an obstacle comparable in size to its own wavelength, the wave fractures and spreads into the space that should be dark. We call this phenomenon diffraction. The results of this wave bending are visible every day. As light reflects off the microscopic grooves of a compact disk, the waves diffract and separate into distinct color patterns. Diffraction also creates the glowing boundary visible. When intense light hits the edge of a dense object, such as sunlight spilling over the top edge of a cloud. To map the mechanics inside these shadows, we have to look at what happens when light hits a very sharp edge or a microscopic gap. At this scale, treating light as a series of straight rays fails. We must rely instead on the geometric behavior of the waves themselves. Measuring diffraction from a standard light bulb is mathematically chaotic. The source emits expanding spherical waves, meaning the distances and angles change at every point simultaneously. Physicists simplify this through the Fraunhofer approximation. This method forces the waves to travel as flat parallel planes rather than expanding spheres. We achieve this by placing a point source of light at the exact focal point of a convex lens. As spherical waves pass through, they emerge as synchronized parallel waves, traveling forward until they hit a solid barrier containing a single narrow slit. Because every ray entering this slit is parallel, we can use straight-line geometry to predict how they will interact at a distance. By controlling the initial chaos of the waves, the Fraunhofer setup provides a clean two-dimensional canvas to calculate the geometry of light. Inside that slit, Huygens' principle dictates that every microscopic point within the opening acts as a brand new source, emitting its own secondary wave. We track parallel rays emerging from the slit, directed toward an observation angle on the screen, defined as theta. Leaving at an angle means traveling different distances. Dropping a perpendicular line from the top edge to the bottom ray reveals this extra distance, the path difference. This tiny geometric discrepancy determines the entire pattern. It dictates whether the crests and troughs of these infinite waves will align to build each other up or fall out of sync and destroy each other. The angle of observation creates a physical lag between the waves, forcing them into a state of continuous interference. In standard wave physics, a path difference of exactly one wavelength aligns wave crests perfectly, amplifying the light. In a continuous single-slit, a path difference of one wavelength creates darkness. Dividing the slit in half, we isolate two rays spaced exactly halfway apart. Their path difference is half a wavelength. They perfectly destructively interfere. This pairing cascades infinitely, canceling every ray. When the total path difference reaches an integer wavelength, continuous apertures sabotage themselves by matching every ray with a neutralizing partner. If we shift the angle so total path difference equals 1.5 wavelengths, we divide the slit into 3 segments. Rays in the top and middle segments pair up, perfectly canceling each other. The bottom segment's rays survive, hitting the screen to create a bright band. This bright band is significantly fainter than the light at the center of the pattern. Because 2/3 of the light energy was destroyed inside the slit, only 1/3 reached the screen. Maxima only appear at angles where the geometry is uneven, leaving a fraction of the waves without a neutralizing partner. Mapping our proofs reveals the final pattern, a massive central peak, zero intensity at integer wavelengths, and decaying secondary peaks at odd half wavelengths. At 5/2 lambda, the slit breaks into 5 parts. 4 cancel, and only 1/5 of the intensity survives. One final variable determines the shape of this graph, the physical width of the slit, represented as A. Decreasing the width squeezes the waves into a narrower space, which forces the resulting pattern to stretch and spread out wider. Restricting the wave's physical boundaries makes its wave nature more pronounced. These single-slit equations require an inversion of the logic used for double-slit interference. In this system, integer wavelengths guarantee complete destruction, while it is the odd half wavelengths that allow the light to survive. Light operates as an infinite self-interacting field, with every point in the aperture interfering with every other to navigate the physical bottleneck. The straight lines of ray optics are simply the convenient shadows cast by this more complex microscopic reality.